Okay, so I'm going to continue with secure messaging today. I don't have any notes, but if you guys have any logistical questions, I can take those first. Nobody? All right. So, all right, so just to recap from last time, I'll just start from kind of the beginning. So we've got SMS, right? And the thing that we know about SMS is that it's not end-to-end encrypted. Because here with SMS, we're encrypting to the server or to the provider that we're using for SMS. And then they can see the message, they can store the message, anybody that attacks their system can see the message. And we actually don't want to give all of that trust to a third party. We want to be able to delete our own messages and then we're done with them. So these are encrypted, but only to the provider, which is, the issue that we're having. And like I said, the provider can see and store the messages. And then we spoke last time about a few properties that we might want from a protocol that gets secure messaging. So properties we want. What are these? We want confidentiality, right? That's the end-to-end encryption part. We also want usability, right? If we're going to make sure that this is a thing that people can actually, move to for a lot of their communication, especially, instead of being in retrospect, being able to move to something like this before there's a problem, then we need usability to be one of the chief concerns. Yeah.
On that usability point, is it possible for end-to-end encrypted platforms to have something like a password reset?
In what sense?
Well, like any account you have, you can reset the password by putting in your email and they forward you a token, and even though you don't know the old password, you change it, right? And then how would that work with keys without storing them on the server, right? If you lose your device, can you get your old account back?
You cannot get your old account back. Okay. And the reason that's true is exactly for security, because if you could get your account back, then there's some way to kind of, without knowing your key, recover the information that you would need to get all your old messages, which you don't want.
Is there some sort of research being done? Because that's like a big usability flag.
Sort of. If you want all your messages stored somewhere, right, and you only care about briefly in transit, but then you don't care that people can see your messages in the future, then just use iMessage, right? What does iMessage do? It's going to encrypt the message. And then, it's going to get to your phone. It's going to be stored. You can say back up to the cloud. And then they're going to be all stored in plain text on the cloud, and anybody can grab them, including you, which is, that's fine. And that kind of is covering the usability concern you're talking about, that people want to be able to recover their messages. But if you can recover your messages, then other people can recover your messages.
Well, so I'm talking about more like just the account, right? You message me now. I have my account in your contacts.
Right.
If I lose my phone account back, such that I don't have to give you my new
number. Let's see. I believe the way that Signal works with this is, as long as you're on your same number, then if you get a new phone, you'll just start a whole new key. And then everybody you're talking to will get a message saying your key with this person has changed.
Okay. That is when you have a lock the number. You can lock the number.
Yeah.
Don't let anyone else take this number.
Yeah.
Okay.
Yeah.
All right, thanks.
So we've got usability. And then last time we spoke about the setting that we were in, right? Which is the asynchronous setting. That is not how you spell that. Asynchronous setting. For which we're going to run into some concerns. We're going to run into concerns of, asynchronous setting means we're going to have reordering or dropping of messages. which means we want immediate decryption, which is that you don't need the entire message chain to decrypt the most recent message that you received. And we're also going to want the ability to know what order your messages are supposed to have been received so that you know what order the person sent them in. Turns out you're going to need this ability to order the messages for immediate decryption as well, because you need to know which key to use. But these are some of the things. And then we've also got a couple other concerns. Maybe I can move this whole situation up slightly. Oops. Yeah. There we go. And then we wanted forward secrecy, right? And you've heard this term before in the setting of TLS. And what was the last one? Was post-compromise security. And this is just healing. So these are the properties that we want, and we'll go through some of the protocols that we thought about last time and what they're doing about these properties. So the thing that we spoke about last time for encrypted email, this is kind of the same picture from last time. It's the same thing that also iMessage does, except for the fact that I think I had an error. So especially for encrypted email, right? You're signing the message. This is something that we covered earlier. You're not actually signing the ciphertext anymore. iMessage at some point used to sign the ciphertext. I don't know if that has changed. I'm guessing it has, but I can ask Gabe and post that at some point. So the only difference from last time's notes is that actually the signing should be of the message. I thought last time when I came to class that encrypted email for a lot of different encrypted email apps and iMessage used to get this wrong. I don't know. I think that they get it correct now. I will have to confirm that though. But this is kind of the overview. We spoke about this on Tuesday as well, which is that, you know, both parties have these keys, and if you kind of ignore the symmetric encryption that we're doing just for efficiency's sake, then you're just pulling the other party's key and you're encrypting your message under that key, you're signing the message under your own key and sending it across. The problem here is that these keys are long-lived. So that's why kind of you're going to run into some issues, right? You're not going to have healing. You're not going to have forward secrecy because you're never changing your keys. So once an attacker compromises you, everything that happened before then that you could see, the attacker can figure out. And this kind of functions under an important assumption, which is the fact that the attacker can see every message that you're getting over a channel. So the attacker could like tap whatever channel you're getting the messages from and store all the ciphertexts and all the signatures. And then now the attacker can do this as soon as they get the key. Does that make sense? Why this is not giving you forward secrecy? Long-term keys, yeah. Okay. Okay, so let's talk about the properties we want and what we're getting from iMessage and what we're getting from encrypted email. So these were the same ones from the first slide. It's the same properties. This is what we want. What's happening in the case of, let's start with maybe encrypted email. So do we get confidentiality just initially? Does anybody in the middle for encrypted email, just like basic confidentiality when you send one message across? Why not?
Well, you know who you're talking to because the email's going to go somewhere, right? So you have the email, the source and destination emails.
You have the source and destination emails, but confidentiality is of the message, right?
Okay, but not the metadata.
No, metadata, we're not going to hide metadata here in this class either. Yeah. Confidentiality is off the message. So here we're just talking about the messages themselves. You're going to need kind of, when you're pulling these keys, you're going to pull the keys of the person that you're wanting to talk to anyway. So that metadata is gone. Like that's a lost cause here. Confidentiality, encrypted email, we are actually getting confidentiality because we have the keys, right? Like I'm going to share the key using PGP basically with somebody else that I know and trust. And so I know that unless somebody compromises my key, my messages to the other person are secure, right? So that's why we're getting confidentiality. Usability is kind of, you guys tried sending encrypted emails, so you probably have more to say about usability. Um, it's doable. And then all the rest of this, these two things aren't really handled, right? So they're not concerns for, like, they're not even trying to handle them. And then these other two things don't come up because we're never changing keys. So, you can always decrypt messages as and when they come in, you're fine. This kind of thing of immediate decryption comes in when you're trying to use a different key every single time you encrypt a message. And then you have to know which key. And you'll see it'll actually come up a little bit more for Signal because the way that Signal works, you're only able to generate keys in order. So what's happening with encrypted email is every single time that I'm encrypting a message, I'm picking a new message key. So all of my message keys are disjoint from each other. They can all be kind of retrieved using the secret key of Bob, right? That's what I'm optimizing for. But the actual message keys are disjoint, and that's not going to be true in Signal anymore. And that's how we're going to get forward secrecy, actually. Okay. So these aren't concerns. And then, like, similarly, these are not concerns for iMessage either. It's a very similar protocol. Usability now is not bad, right? We all use iMessage. It's fine. It works. What about confidentiality? Do we still get confidentiality? Maybe. I hear one maybe, which I agree with. I don't know if everybody agrees with that in this room. The reason why it's a maybe, let me try to explain that a little bit, is because you're not sharing your keys, right? There's somebody else kind of sharing your keys for you, which is the Apple servers. So what happens if Apple just decides to, give the person who's trying to talk to you a different public key, right? Now they can man in the middle you, right? We learned about key exchange a few different times in the class so far, that you can just completely man in the middle key exchange, right? Because you don't share keys yet. So you have to, first create a shared key and then talk to the person. But here it's questionable, right? Apple could very easily just decrypt messages on their end and re-encrypt them under your key and send them to you, and that would be.
It could be backing up by iCloud.
Or the recipient could be backing up to iCloud. Yeah.
Back up their messages.
Yeah, there's lots of people who back up their messages, right? Like this is common practice. My mom does it. She refuses to stop. It's fine. So this is, you can't always stop people from backing up their messages, and that can be a problem. But I think the reason why I was focusing a little bit more on the storing of the keys and who's distributing the keys is because technically, if somebody wanted to find a way to store their Signal messages, they could probably do it. And that would have the same kind of problem.
Encrypted ones?
Mhm.
The unencrypted messages? You can back up a Signal database, but it's locked. It's encrypted with whatever you use.
So with Signal, the way you're getting forward secrecy is by deleting the keys.
Right.
So you could back up the ciphertext and like you've lost all the keys, so you can't decrypt them. But I mean, you could send somebody messages and they could decide to screenshot them or kind of save the conversation. And that's going to be a problem in a very similar way. We can get rid of that, right? Like we can stop storing messages to the cloud in iMessage. I agree with you that actually, because iMessage does this kind of natively, that they always store your messages unless you tell them to stop. It's a bigger problem because, a user is much more likely to just not make decisions than they are to go ahead and make the decision to stop storing their messages in the cloud. But the point with storing the keys is that you can't change that. Apple's not going to give you a way to, provide your own keys to its app. This is not a thing it's going to do. Apple rarely lets you decide what you're doing with your own devices. So, Okay. So we spoke a little bit about what forward secrecy and post-compromise security are last time. And post-compromise security perhaps is kind of the easier one to describe, right? Which is just you get attacked and then in the future you want to be secure again. This makes sense, right? Like everybody, at least when we were much younger, I don't know if this is true for everybody in this room actually, now that I'm saying this, because I realize I'm slightly older. When we were much younger, like there were things that you clicked on and then you're worried that now somebody has access to your computer, or, you know, there's viruses on your computer or something of that sort. Little bit less scary now, I guess. There's a lot more protections in place. No, it's a little bit less obviously scary. You know, you don't like click on a thing and then your entire computer just like grinds to a halt. It's much more kind of happening in the background, but basically we know that we get compromised. You know, like at least I know for a fact that, you know, my grandparents' computer gets compromised every once in a while. Like this is a thing that I can guarantee. I want that there will be, you know, healing from that compromise eventually, because like that's the best we can hope for. Also, you know, if there's an attacker, say, you know, the government is trying to listen in on your conversations, if you're healing from that compromise, it like really changes the amount of effort they need to put in to compromise your messages, right? Like now they need to compromise your messages and then they need to keep doing that over and over again to keep reading your messages. And that's good, right? That means that it's much less likely that they can, it reduces the scale at which they can do it, which in some sense is all we can do. So this is just healing from compromise. And then we've got forward secrecy, which is a little bit more complicated, but it's kind of saying that everything that happened, you know, the past is in the past, basically. Anything that I did in the past, if it was secure, I can just forget about it. So this is the past is in the past, right? So as long as you've deleted the messages. Right. Okay, so this is forward secrecy and post-compromise security. And the whole point of forward secrecy is to make deletion meaningful. Okay, so now the key ideas, Signal is going to try to achieve all of this, all of these properties that we've been discussing. And the key ideas for Signal is, you know, we know from before already that you can use symmetric encryption to encrypt all your messages as long as you know that each of these keys is different and nobody can get these keys, then you're fine. You can use these keys. You can generate a new key for each message. So that's great. Let's try to do that somehow. But we want to do that now in a way that satisfies forward secrecy. And we're going to do that using this KDF that we spoke of before, right? So the first key idea is just kind of doing this in a way that satisfies forward secrecy. And we started this last time. And then the second key idea is finding a way to heal after compromise. This is going to be the slightly more complicated part because we're going to do a lot of different Diffie-Hellman and key exchanges, but we also don't want parties to have to be online at the same time. And like that's like the entire problem with healing from compromise is we don't expect people to be online at the same time. And this is reasonable, right? Usually you're messaging somebody, you don't expect them to be free at that point in time. You don't even expect their phone to necessarily be switched on, right? People switch off their phone sometimes. So you can't expect this because if you need everybody to be online at the same time, very quickly users will get frustrated and then they'll just stop using the thing, right? So we don't want it to require both people to be online at once. And then finally, we'll just encrypt the messages under these, you know, forward secure, post-compromise secure keys. That'll be great. So let's try to get this, you know, let's see how far we can get today in trying to get this. And actually, let me tell you some names of these things with respect to Signal. This is going to be called the symmetric ratchet. because this forward secure piece is going to generate symmetric keys under which you're going to encrypt and decrypt. And kind of the keys going into this chain as well, this like symmetric ratchet, those keys are going to be symmetric. The next chain is called an asymmetric ratchet, and that's because you're going to do this Diffie-Hellman key exchange. And the Diffie-Hellman key exchange is going to mean that the keys going in are asymmetric, right? The keys stored by Bob for a Diffie-Hellman key exchange are different than the ones stored by Alice. The naming of things in Signal is helpful eventually when you're trying to discuss details, but in the beginning, it's frustrating because you have to learn all the names. And then the last thing we're going to use is authenticated encryption. And in particular, we're going to use something called AEAD, which is authenticated encryption with associated data, which just means I can also send some information in the clear, which is authenticated but not confidential. So that part kind of comes at the end. That's just saying, you know, once we both have keys, how should we share our messages? Let's use authenticated encryption, because we already spoke about the fact that encryption can sometimes be malleable, right? But if we are authenticating our messages before we encrypt them, then we're good. And we can also kind of authenticate some associated data with that. So that's what we're going to do. That's like the big idea of Signal. And we now have kind of the KDF, which is like our key component. Signal uses this everywhere. The KDF is like the whole thing with Signal because it's all key management. Once you have keys, then you're fine. You just encrypt your messages. So one of the things to remember about the KDF, just because, you know, you're seeing pseudo-random functions and key derivation functions and stuff for the first time, is that everyone knows the code of the KDF. So the code of the KDF is public. What does this mean? This means that if I have both the inputs, so if I know the KDF key and I know the KDF input, then I can compute the output. The output only looks random when you cannot guess the key and you cannot guess the input. So this is important. It's like one of these has to look random. It has to be indistinguishable from random to the attacker for this to be indistinguishable from random to the attacker. So that's what we're going to try to get, right? We're using these KDF chains. We want somehow that we're able to switch out one of these inputs for new randomness every once in a while. So, okay, outputs of the KDF, you know, appear random to an attacker that doesn't know one of the two inputs, which is like these two things. And what does it mean that the attacker doesn't know? Doesn't know here means indistinguishable from random. Okay. So let's try to get forward secrecy using this, right? We have this one chain. How do we get forward secrecy from this? We spoke last time about how we could just kind of take the outputs of the KDF and just put them directly back in, right? So just like get key 1, use that for a message, and then put that back into the KDF, and then get key 2. And if we had complete like synchronicity, maybe this is okay. But what happens when we get asynchronicity, right? So this isn't it because, you know, what's the problem here? Asynchronicity. Hey, I spelled it correctly this time. Asynchronicity, that's the problem. So what if you get message 2 before you get message 1, right? So the first idea might be just like, don't delete the keys that you know you still need. That might be the first thought that you have. So let's do that, right? So let's, so we get ciphertext 2 here, and then we get K2, right? So we compute K2, which is just like we ratchet forward and then we ratchet forward. But then we say, actually, we still need K1. So I'm still going to store this value. I'm still going to store this particular value. And all I'll do is I'll compute the K2 and I'll decrypt this message. So I'll decrypt under K2, ciphertext 2, and I'll get message 2, and then I'll, be here. And then what happens if the party now gets compromised, right? Is message 2 secure here? Because I'm still storing K1, right? So we can keep doing that, right? So we can also do this for K3, and as long as the person doesn't receive message 1, all of these keys will still be computable from the previous keys. And so that's the problem we're going to run into. And Signal has like a very clever idea to keep around these old keys. And that's one of the key ideas, this symmetric ratchet. Okay, and we kind of briefly went over that before, right? So the idea that Signal has is that we can split the string in half, right? So we said this a few slides ago, is the output of the KDF is long, right? In fact, it's twice as long as the key that goes into the KDF. So we can just take out the key and use the rest as the message key. And then what we can do is we can now store these output keys and keep the new KDF keys going into the chain. And once we've used them, we can delete them. And that'll give us forward secrecy, because we know that if you don't know, the input, you're not going to be able to get the output. And we're going to delete these inputs. So we're going to make them really unknown to the attacker. So that's the idea of Signal. That's kind of happening here. And this is for one person to talk. We haven't still spoken about how 2 people can be talking to each other. But if one person just wants to send a whole bunch of messages and get forward secrecy, we can now do this. We can just generate all these message keys. The sender will just encrypt messages and then delete the keys one after the other after they encrypt the messages. And then what is the receiver going to do? The receiver is going to just store any keys that it still needs. So let's go back to that first thing that we spoke about, which is that we get ciphertext 2 first, right? Then what's going to happen is first we'll ratchet forward here and we'll grab message key 2, or let's say ciphertext 3 first, actually. Yeah, go for it.
I'm not sure I'm following. So how does it provide forward secrecy? What's stored on the?
So I'll actually cover that right now, because I'll go through an example of like exactly what will happen. So we'll get ciphertext 3, right? What we'll do is we'll ratchet forward, get message key 3, right? Once we have message key 3, we can just decrypt. Whoa, what just happened? Sorry about that. So once we get message key 3, we can decrypt ciphertext 3, right? We can just like decrypt under, I'm just going to call this K3 for now, ciphertext 3, and we'll get this. And then what do we do? What do we delete? What do we keep around? So first we'll ratchet, or first we'll kind of, we know we can delete this guy, right? Because we've already used it. So we can delete that. That's good. We know we need KDF key 3 around to get all the other keys. So we'll keep that. But we can now delete this stuff.
Oh, okay. Okay, so you're keeping the message key.
Yeah. So you just take the message key and you store it in a dictionary. You say, this was key 2. I need this for the second message. Everything else can go from before.
Okay. You can't roll the chain back because you don't have KDF.
Exactly. So the KDF is importantly what we call a one-way function. So you can't roll it back just by definition.
Yeah. Okay.
Yeah. Yes.
Does the KDF make the message key and the KDF key at the same time?
Yes. So what we're actually doing is we're taking this long output that the KDF produces and just splitting it in half. It's kind of just a naming thing, but it helps. Okay, so this is the main idea of the KDF, like the symmetric chain that we're going to build from the KDF. And now all we'll do to get a conversation between two people. So how do we get a conversation? We just take two of these. So you'll have one chain that we'll call the sending chain. And then you'll have one chain, which we will call your receiving chain. And so now we have forward secrecy, which is great. That's helpful. But we're still missing a couple of things. One of the things is like we're missing this whole conversation thing that we like to get, right? We like to know where our messages are supposed to be, like which of my messages are you responding to, sort of. And there isn't a total ordering on this, because obviously like each party's view of the conversation is different. I'm sure if you've ever experienced lag on a call, you know this. But there's still some sense in which we can keep parties like in the same general realm. We let people, sometimes your phone will let you know, the other person hasn't received these messages yet or something. So that we can still actually kind of achieve that here. And then the other thing that we're gonna get is post-compromise security, right? We haven't spoken about post-compromise security. We haven't refreshed our randomness yet in any sense. And that's the part that's, really complicated. So we'll try to break it down and see what we can do about getting post-compromise security. And this old picture of what we're doing right now, which is the symmetric chain. And what we want is we want post-compromise security. Okay, so we know, this symmetric chain looks fine. It looks familiar enough. And say that an attacker kind of compromises this entire region, right? So like somebody was sitting on your phone and could see everything here. We want somehow that when the attacker leaves, that this portion of the conversation starts to be secure again. We want that. That would be post-compromise security. Like once we have the chance to refresh our keys, we're really doing that. Notice that kind of the input appeared back in the picture. We were not writing the input before, because for the symmetric chains, we just use a constant input. We just use kind of the all zeros string or something, and we're fine. For the asymmetric chain, we brought the input back because that's what we're going to use. That's where we're going to refresh our randomness, because the thing that we said before was the KDF will give you output randomness as long as either of the inputs was kind of looked random to the attacker. So the new KDF key and the output key are not going to be guessable by the attacker if either one of the inputs was not guessable by the attacker. And so we can kind of try to get this healing in a way that we've seen before, which is just do a new key exchange, right? If you do a brand new Diffie-Hellman key exchange and the attacker doesn't know the secret keys of either party, then you should be fine. So, okay, we'll just do new input randomness. Yeah, do you have a question? No, okay. So we're gonna do, new input randomness via Diffie-Hellman key exchange. So say that we have our, favorite people, Alice and Bob. And they're sending messages back and forth under this one key exchange that they did a while ago. but all of this was kind of compromised. So. So Eve was kind of like dropping in on this conversation the whole time. What we can do is when we get out of that compromise, Alice and Bob can simply just like do a new key exchange and they'll be good to go. But this kind of runs into the problem we said before, which is that they have to both be online. Otherwise, how do we do this? And we can actually do this, which is, we'll talk about that in a minute, but like we can actually do this. It's going to be called continuous Diffie-Hellman. But before that, right, before we run into the problem of both people are online at the same time, say we say both people are online at the same time, where do the keys go, right? So we got these new keys. Where do these keys kind of end up in we had these two symmetric chains, right? Let me remove all this for now. We had two separate chains here. How do we know where to put these keys? Right? Do we put them in here? How do we know that both people are putting them in at the same spot? What if this message never arrives? Right? That happens sometimes. We're assuming that the channel can be faulty. So even if we have this new input randomness, it's not clear where we can put it. Does that kind of make sense? Because I don't know if I've explained it super well, but it's important that this makes sense because otherwise the fix won't really stick with you, if the problem doesn't compute. The problem is just the fact that we could drop messages. And so we don't know where to kind of start this key exchange ever. And the way that we make that more robust is we take this KDF and we just use it again. And we start what we call a root chain. And this root chain will kind of create small sub conversations. So, right at the top of the root chain, you get this like shared key that Alice and Bob had for Alice. And then after a while, they put new input randomness. And after they've done that, they'll create new input randomness for the new kind of like symmetric chains. And they can just start a new symmetric chain from there. And so now, what we can do is we can communicate that Diffie-Hellman key exchange, right? Here we had G to the power A and G to the power B. Here we have new keys, right? We have G to the power C and G to the power D. We can, or at least, like once we refresh this randomness, if we're able to send information back and forth, we can just do this with every single message. So every single message here can contain these public values, right? Because the public values are public, and as long as you get one of them, you're able to use the root chain to compute these shared keys, and you're able to kind of move forward from there. And this is a little bit complicated, but Gabe will go over this whole thing again as well. It just helps to see it multiple times because there's not a super linear way to present this. So you kind of see a bunch of the fixes at, like one by one, but they really make sense only together. So finally, we're going to do a continuous Diffie-Hellman key exchange, and this will kind of help you see what I meant by this, sending the randomness over and over again, is to not require Alice and Bob to be online at the same time. We're going to refresh only half the randomness. So this is just like your standard key exchange so far. And now both parties have G to the power AB. But then what we can do, because we already have this shared key, is just refresh half the randomness. So when Alice decides, hey, you know, I want to refresh my randomness now, Alice can go ahead and say, here's a new key, you know, here's a new public value. And Bob can go ahead and update the key that he was holding. So he can go ahead and do, you know, this situation over here. And then once Bob says, okay, I want to refresh my randomness also, he can send over G to the power D, and then we end up with a brand new key, right? This is the whole idea of the continuous Diffie-Hellman key exchange, is each party, when they send a message, can update their half of the Diffie-Hellman key. And so if this step over here was compromised, then this step will also be compromised. But this step will be fine again. So, I mean, this step isn't exactly compromised, but it's kind of not fully secure, right? So if we're here and the compromise was on Bob's end, right, and not on Alice's end, then when we ratcheted forward here, we're still in trouble, but we know that that trouble is going to go away soon, right? Because Bob will go ahead and, you know, once Alice sends new randomness, Bob's going to say, oh, I guess I'll send new randomness also. And Bob will go ahead and update, you know, their own randomness, and then we're good to go. Then now here we're in the clear. So that's continuous Diffie-Hellman key exchange. And then we finally just end up using this continuous Diffie-Hellman key exchange in this like KDF chain. Now, I'm sure you guys have a lot of questions. The question that I was kind of thinking of was like, how do people know when to refresh their randomness? This is kind of the last piece, technical piece that I need to cover. But if you have questions about now this, why this might give you, so if you forget about the KDF chains for a second, do you see why the continuous Diffie-Hellman gives you both forward secrecy and post-compromise security? Yeah?
Yes.
Okay, cool. So this gives you forward secrecy and post-compromise security. We want to now use the KDF chains we had before to, you know, get forward secrecy in a fine-grained way, and also get this robustness to asynchronous messaging, where we were decrypting a bunch of messages out of order, being able to reorder them and deal with losses. And we'll just use the KDFs like we spoke of before to do that. So I'll actually go and just pull the chain that we were talking about before. Yeah. So let's get this idea. So this next bit's going to be a little bit complicated, but we'll get through it, I think. If you're with me so far, I think we'll be fine. So each party is going to need 2 of these. We're just going to remove these names for now, because everything's going to get new names. Okay, and then let's call this descending chain. So we'll call the blue ones descending chains. And actually, we'll call the blue ones Alice's ascending chain. And then we'll make maybe green ones for Bob's sending chain. So we've got Alice's sending chain. And we've got Alice's receiving chain. Okay. So good so far. And then we're gonna create a third chain here that every once in a while will tell Alice and Bob. Let me actually copy paste this. I already have this picture. Oops. So we're gonna put one in the middle. And we're gonna call this the root chain. So this is kind of gonna be the complete signal protocol is gonna look something like this. So you'll have a sending chain and you'll have a receiving chain. And every once in a while, the root chain will mandate an update. So right now, say this arm of the root chain gave us Alice's sending chain, and then this arm gave us Bob's sending chain. Then the next time we ratchet forward using continuous Diffie-Hellman, we'll get a new chain for Alice. So once we do this, we're just gonna, let me try to duplicate this page maybe. Ah, that was great. So once we get the purple output, we're just gonna take all of this and we're gonna restart it with this. So we know we have this starting key, right, over here. We're just gonna make that the output from here. So we're gonna take this output and put it here. And Bob's gonna do the same thing so that they both share the same key. The purple go. There it went. Okay. Is that how does that seem?
Who goes first?
Who goes first? That's a very good question. That's what we're gonna do right now. Does it make sense that if we did a continuous Diffie-Hellman, we were somehow able to get the root chain to give us these keys using the continuous Diffie-Hellman, then we're getting forward secrecy. And then these pieces over here that we have are gonna give us this asynchronous messaging that we want, where we can go forward and get, like the fifth message that you sent me in a row, I can decrypt that first, even if I get that first.
So how are these subchains different from the root chain? Because if you cycle forward in the KDF, right, you got Bob's, he's got his sending chain, right? Isn't the next element of Bob's sending chain the receiving chain, the sending chain for Alice?
Here?
Yeah, wouldn't that just be Alice's root now?
No, so we actually, these are three separately keyed chains. So these things, the purple ones have the same root key. The green ones have the same root key. And the black one has the same root key for both parties. So there's three different chain keys that are, yeah.
So the root key for Alice and Bob will be the secret key, right?
The root key for Alice, there's a few different secret keys. So there's the root key for Alice and Bob, and then there's the sending chain keys for Alice and Bob, and the receiving chain keys for Alice and Bob. These are all secret keys that we use for the KDFs. And then the sending and receiving chains will spit out all of these message keys that are also secret that are going to be used to encrypt the messages.
Why do you have to make it so complicated?
To get all the properties. Like if you actually, so this is actually something that Ron and I thought as well. So Ron Panetti at the BUSEC, he has been working with me on this project for 3 years on like analyzing the security of Signal. And the first thing we said when we started the project was this seems too complicated and it seems kind of redundant and it doesn't make sense why we need all of this. So, maybe we can cut away pieces of it and we'll still get the same security. Let's try to do that. And we actually spent half a year in meetings talking about different ways to either break the protocol and show that the redundancy hurts it, or cut away pieces and say that the security still holds. And we haven't found a way yet. So it at least seems to us like the complication is both necessary and sufficient for the properties that Signal's protocol is trying to achieve, which is great news in some sense for Signal and terrible news for anybody that has to learn the protocol. But the good news for you guys is that since I've done this, I'm happy to discuss like all the different ways that you're thinking of to do something that's less complicated. Because in my opinion, that's the best way to learn about this protocol is like, think of all the things you could do that you think are better and think about why that doesn't work. Because once you've done that 2 or 3 times, it's going to be so much harder to forget Signal's protocol. Because you realize that you really can conceptualize then why it's so hard to solve the things they're trying to solve. And like why their solution seems really complicated the first time you see it. But the 3rd or 4th time you see it after you've tried to attack it, it starts to seem a lot more elegant. You're like, this is a great idea. Yeah, go for it.
So I'm not sure why not just have one chain? Why the root chain and the sending chain and the receiving chain? Well, having 2 different chains is good for sending and receiving in case something gets dropped, but why the root chain?
Why the root chain? So the root chain is for this thing that we were talking about, where do we put these updated Diffie-Hellman keys, right? So we're kind of updating the randomness in these steps here. If we were just updating the randomness just in the ether, like say they're just doing a continuous Diffie-Hellman in the middle instead of a root chain, then they don't know kind of, so let me remove the root chain, right? So now you're sharing new Diffie-Hellman keys, but where do you put them?
Okay, that's the problem. Okay.
Right? Like which part of these like sending and receiving chains will get this root key? And how do you communicate that to the other person?
Don't you still have the same problem though?
You don't, because you just start a whole new chain. So you say, maybe, I'm still waiting for messages from the old chain. I don't know. But I'm going to get a whole new receiving chain because Alice has updated her randomness. And I know that she's only going to send messages on this new chain now.
Wait, but can't the root chains go out of sync, right? Like whatever message and messages in like an API call.
Yeah.
The message cycles the chain. That can also be dropped. So I feel like you still have the same problem.
So the problem is resolved by the fact that what you do is in every single message in this new chain, the like authenticated clear text, right, that's not encrypted, is going to give you the new public half. So say that to move to this purple chain, Alice had to send over this new like public half that's G to the power A prime. Every single ciphertext that you get here, so you're going to get ciphertext 1 with G to the A prime. Ciphertext 2 is going to have G to the A prime. Ciphertext 3 will have G to the A prime. So the second you get any of the messages in this new sending chain, you just put G to the A prime in the root chain and you can kind of compute the right message key here.
Okay, so all the messages in that root chain will have G to the A prime, the same G to the A prime.
Yeah, the ciphertext will have that with them. Yeah. So that's going to be kind of the associated data. This is why we needed an authenticated encryption with associated data, as opposed to just an authenticated encryption, because we actually need this message, like this part of the message, we need it to go out in the clear.
Yeah, okay. So you, in order to cycle the loop chain, you need the messages. You can't not send something.
Yeah, you only cycle the messages when you get a new, the chain when you get a new message. But the thing that's interesting is I believe the way Signals protocol works, it's not, I'm not 100% sure. So if somebody tells you otherwise, maybe believe them. But I think when you get read receipts, that counts as a new message. So that will cycle your chain. So you're actually getting post-compromise security very, very quickly.
Okay.
Yeah. And then there's still actually a small piece that only becomes clear why it's a problem when you're thinking about exactly when to do these updates. Because it's not clear when to do the updates. You don't want to be updating kind of too quickly for the other person to catch. Say like one person keeps updating over and over again, then you don't know how many updates have happened before you get to start sending messages. So you'd have to wait to get all their messages before you can do anything about it, right? And so actually for that situation, we do this thing where we wait for an update before we update our key again. So when I get a message from you that has a key that I've never seen before, then I know that you're not going to update your key anymore till I send you a message with an updated key.
Okay.
Yeah. That's like honestly the last detail. Like genuinely after you've learned this update rule, that is the entirety of the Signal protocol. I will put these notes up online. Gabe will cover the protocol again in the next 2 classes. And I'll link you to Signal's website, which also has like a pretty comprehensive description of all this. It's still going to be complicated. It's going to take a few tries. If you really want to understand the protocol, the lowest cost way to do it, the like least energy you can spend is just try to attack the protocol and see what breaks. And if you can't see what breaks, then talk to your friends. If your friends can't see what breaks, go to office hours or, you know, come to lab and ask me about it. Because once you've done that twice or thrice, like Signals protocol will really start to just like set in why they're doing the things they're doing. I learned this in my Young's class, which was like the applied cryptography class, and it went straight out of my brain after the class, or even like before the class had ended. But after I like started discussing it a little bit with Ron from this perspective of it seems redundant and, you know, what if we can break it? Then suddenly it was much harder to forget. Awesome. That's going to be all for today. Have a great weekend, guys.
PDF. Does it take in 2 inputs and 2 outputs?
Which one?
So for this